Hello, I'm your host Shakil Khan. In this presentation today, I'll talk about the design, analysis, and simulation aspects of my AC phase control system, which I have implemented using a Raspberry Pi controller and some custom-built hardware. On the agenda, we'll have these 4 topics. If you want to reduce the amount of power going to an AC load, one way to do that is by clipping the sine wave. What I mean by that is we'll look at the next slide, and so here are 2 waveforms, and these were generated on my system. The top wave, this is a full sine wave, and the bottom one, as you can see, parts of it have been clipped. If we trace this cursor, and this is where a zero, this is where the zero voltage is happening, or also this point is called a zero crossing point. Microcontroller is keeping track of this, and it's adding a delay, whatever is configured in the program. So in this case, this is a 6 millisecond delay, and then it lets the track, or the quad track in this case, conduct for a little while, and then we have another zero crossing, and then again the delay is added, and this pattern repeats. The AC phase control system consists of 3 subsystems: a zero voltage crossing detector, which is mostly the top part here, Raspberry Pi microcontroller, which is over here, along with the details of the GPIO port, and the last one is the quad rack driver over here. Let's start with the zero voltage crossing detector. So we start here. We have the line voltage coming in at 110 volts 60 Hertz, or I believe it's 120 volts. That's reduced to 28 volts using a step down transformer. Then I use a voltage divider to reduce it further to 4.2 volts. Then we have a current limiting resistor here. The signal is going into the inverting input of the op-amp. The non-inverting input is grounded. I have 2 clamping diodes here. This is to prevent the op-amp from excessive voltages happening at the input. These diodes will clamp the voltage to plus 0.7 or minus 0.7. The op-amp power supplies are, the positive one is connected to 5.2 volts, and the negative one is grounded. How the op-amp functions is simple. If the non-inverting signal voltage goes above 0, the op-amp will saturate to 5.2 volts, or if the input signal voltage is 0, or if it remains below 0, then it will remain at 0 volts. So basically that will give us a square wave, and I'll show you a picture of what that looks like. The output from the op-amp will go to a GPIO port on the Raspberry Pi controller, which is from here. However, I have decided not to send this directly to the GPIO port. Instead, I'm using a pull-up resistor and a transistor, and the power supply from the GPIO ports. So port 1 can supply 3.2 volts. I take that, and I'm using the op-amp signal to drive the transistor. Since this is a square wave, it's easy to drive this transistor into saturation or cutoff. When the transistor is conducting, this point gets grounded, and the GPIO port 13 will see a 0, and when it's not conducting, it will see the 3.2 volts and it will go through this current limiting resistor. So that's how I'm safely giving it the zeros and the ones. Next, we'll look at GPIO port 11, which is providing a control signal to fire the quad rack. As you can see, the same deal here. I'm not sending it directly to the quad rack driver circuit, because this side we have the high voltage, high AC voltage, and so I wanted some separation to protect my microcontroller. So hence I'm using MOC 3010 triac optocoupler chip. So this is the input side of it, and this expects 1.2 volts for this diode to turn on, and hence I'm using this voltage divider here, and when it gets its 1.2 volts, it starts conducting, and the output also goes into conduction, and that's how, and it triggers the diac, and the diac in turn will trigger the triac, and the current starts flowing to the AC load. How I built this quad rack driver is I took a commercially available AC dimmer switch and modified it a little bit. So this one has a quad rack, which is a triac and a diac combination, and here we have a capacitor across the load terminals. This capacitor and the inductor is to smooth out electrical noise, whereas this resistor capacitor combination is for timing. It's a RC circuit to provide timing for the diac trigger. So these 2 points used to be connected, but I have modified it slightly so that now this goes through this optocoupler, and I can control it using the microcontroller, or the program running on the microcontroller, and it works pretty good. So yeah, and then I've selected the resistor value so that this time constant is way smaller than the time period of my AC signal. In this section, I'm going to talk about the software simulations that I've done during the analysis or the design phase of building the AC phase control system. The package I have used is called TINA. This is TINA version 10.1, and it's made by a company called DesignSoft. TINA is a very powerful package for the design, analysis, and simulation of analog and digital circuits. It even allows you to simulate microcontroller units, and comes with a very extensive set of libraries for various components and parts. It even allows you to import your own SPICE models if you like. Yeah. So what you're seeing on the screen, this is a simulation I did of the zero crossing detector system. Yeah, and one of the reasons I did this simulation was to see how much power the resistors are consuming, so that I can buy them with the proper power ratings. Yeah, so I have explained the circuit earlier in the presentation. So this is the AC voltage, and I step it down to a lower level, and then it goes, and some power is dissipated in these resistors, and then through a current limiting resistor, this goes into the operational amplifier, and the inverting non-inverting side is grounded, and we have the coupling capacitors. So it's a similar setup, and now I can turn the transient analysis on, and now I can see the behavior of the circuit in real time. It's kind of difficult to, this is one way of looking at it, but a better way would be to look at the waveforms. So I can go to analysis, and if I do a transient analysis for 60 milliseconds. We'll see what that looks like. So all the points of interest where I wanted to do these measurements, I have labeled them. So this is the op-amp output, and yeah, you can see this, and these are the power consumptions on. These are the watt meters and the step down voltage. So I have all the details here. So this was very helpful for me to visualize what the circuit behavior would be like. So yeah, this is in a nutshell, this is what this TINA circuit simulator can do for you. In this section, I'm going to talk about the Python script that runs on Raspberry Pi controller and does all the soft controls. The purpose of this script is to detect zero voltage crossings and issue control signals to activate the quad rack. So this is where the script starts, line 14. We come in, the first step is to import the GPIO, or the general purpose input output libraries. This is a set of very powerful libraries, some very powerful methods that you can invoke. With that, you need to do very little coding, as you can see in the script. After this, I'm importing some time and date time libraries. Then we come to line 20. I am declaring here that I want to use the actual pin numbers on the microcontroller board. Next step is line 30. I'm setting GPIO port 13 as an input port, and also configuring it to use an internal pull-up resistor. Step 24, line GPIO port is 11 is configured as an output port. Next we have I want this to be an event-based thing. So we are using the GPIO library method wait for edge. So basically we are telling that we want to wait for a rising edge or a falling edge of the pulse event to happen, and we want to get notified when those events happen, a rising edge event or a falling edge event. So that's what line 30 this routine does. After this, a couple of initialization steps here, and the program goes into a while loop. I'm going to ignore these 3 lines, just introducing some sleep here to prevent debouncing issues. Then I invoke the event detected method to see if an event has happened. If an event has happened, then the first thing I do is to stop conduction. If it was conducting before, then we want to stop conduction. Then I invoke some date time routines. This is to get the current millisecond in the current second or the microsecond. This is more for debugging purposes. I wanted to see that these events are actually happening at every 8 or 9 milliseconds, because the total AC time cycle is 16.6 milliseconds. Some more logic here is to handle the rollovers for the millisecond counter. So this is where the actual step happens. So I'm adding a delay of 0.006, which is 6 milliseconds, and then firing the quad rack after that. So if I show you a picture of this, so this is what this is that 6 milliseconds coming from, and then the quad rack starts conducting. Well, that's what the Python script does in a nutshell for soft controls. You may also want to watch my other video, which is about the physical implementation details of the system. Please follow the URL if you would like to watch it. I hope you have enjoyed this presentation. Thank you for your time.